Let us begin very gently, and let us begin with a question that at first sounds almost too simple. Why do we speak of spacetime at all? Why not continue speaking, as classical mechanics often does, about space on the one hand and time on the other, as if they were two separate stages on which nature performs its motions? For a long time, that older picture seemed not only natural, but unavoidable. Space appeared to be the arena in which bodies have positions, directions, and distances. Time appeared to be something else entirely, a universal background clock, flowing evenly and independently for everyone. In that older view, one could imagine the world as a sequence of spatial arrangements, one arrangement after another, all ordered by a single shared time. This picture is comfortable. It matches ordinary experience. It matches the way we speak in daily life. We say where something is, and then we say when it happened, and these feel like different kinds of information. We imagine that there is one true present moment spreading across the world, so that even distant events are either happening now, or happened before now, or will happen later. In this way of thinking, time is universal, and simultaneity seems absolute. And yet, when physics began to take seriously the principle that the speed of light is the same for all inertial observers, this comfortable separation began to crack. It did not crack all at once in the imagination of ordinary life. It cracked at the level of careful measurement, careful reasoning, and consistency. One found that different observers, moving uniformly relative to one another, do not agree on what distant events occur at the same time. This is one of the deepest turning points in modern thought. It is worth repeating. Different observers do not, in general, agree on simultaneity. The idea of one universal present, spread across all of space, no longer survives. And once absolute simultaneity fails, the old separation of space and time also begins to fail. Because if one observer says that two distant events happened at the same time, while another observer says they did not, then time cannot simply be a single common label attached to the whole universe in the same way for everyone. The very act of assigning times depends on the observer. The same is true for spatial positions. Distances measured between events may also depend on the frame in which those measurements are made. What remains stable is not the separate measurement of space or time taken alone, but a more unified structure that involves both together. This is where spacetime enters, not as a decorative abstraction, not as a formal trick, but as a natural language for the world once high-speed physics is taken seriously. Let us pause and reflect. The idea is not that space disappears. The idea is not that time disappears. Rather, the deeper insight is that they belong together. They are woven into one geometric structure. Different observers slice the structure in different ways into what they call space and what they call time. But the underlying whole is one thing. This is a very beautiful shift in viewpoint. What first feels more abstract is, in an important sense, more concrete. We are no longer trying to force the world into categories that only work approximately. We are instead accepting the geometry that nature itself seems to prefer. So when we speak of spacetime, we are not merely using more sophisticated language for the sake of sophistication. We are describing a genuine unification. We are saying that the world is better understood as a set of events arranged in a four-dimensional geometric order, where three aspects correspond to location in space and one aspect corresponds to location in time, and where the relation between these aspects is subtler than in ordinary Euclidean geometry. Now let us move slowly into the first basic object of this subject: an event. An event is, in the simplest possible words, something that happens at a place and time. A flash of light emitted from a lamp is an event. A particle collision is an event. A clock ticking at a particular moment is an event. The arrival of a train at a station, if specified precisely enough, may be treated as an event. In relativity, events are fundamental because they are concrete occurrences. They are not just places. They are not just times. They are place and time together. This is important. A spatial point by itself is not yet enough. A moment by itself is not yet enough. Physics concerns occurrences, and occurrences happen somewhere and sometime. Now, once we have an event, we would like to describe it. To describe it, an observer assigns coordinates. These coordinates are labels. They tell us where and when, according to that observer's chosen frame of reference, the event occurs. It is worth repeating that coordinates are labels. They are not the event itself. This distinction matters enormously. The event is something real in the geometric and physical sense. The coordinates are a system of description. Different observers may assign different coordinates to the same event, just as two mapmakers may use different grids for the same landscape. The mountain does not change because the map changes. Similarly, the event does not change because the coordinates change. In relativity, this point must be repeated many times because beginners understandably become attached to the coordinates. One sees numbers, one calculates with them, one begins to feel that those numbers are the reality. But they are not. They are observer-dependent descriptions. The event is invariant as an occurrence. The coordinates are not invariant. Now let us say a little more about reference frames, especially inertial frames. An inertial frame is, roughly speaking, the perspective of an observer moving with constant velocity, neither accelerating nor rotating in the relevant sense. Within such a frame, the laws of special relativity take their cleanest form. One can imagine a network of synchronized clocks and rulers extending throughout space, all at rest with respect to one another, and this entire arrangement constitutes a frame for assigning coordinates to events. Again, there is something subtle here. Even the synchronization of clocks, something that sounds so innocent, depends on the frame. To say that clocks at different places are synchronized is already to adopt a convention and a physical procedure tied to the observer's state of motion. So when one observer says two distant clocks read the same time, another observer moving relative to the first need not agree. This is not a defect. It is the lesson. Coordinates depend on the observer, while the event itself does not. Let us let that settle, because it is one of the central ideas of all relativity. Now that we have events and coordinate systems, we are ready to speak of Minkowski space. Minkowski space is the mathematical model of flat spacetime. It is the setting for special relativity in the absence of gravity. One may think of it as the simplest spacetime geometry, the analog in relativity of ordinary flat space in Euclidean geometry. At first glance, Minkowski space resembles a four-dimensional extension of ordinary geometry. There are points, which we interpret as events. There are coordinates. There are straight lines, which represent inertial motion. There are geometric relations between points. In that sense, it feels familiar. But the familiarity is incomplete, because the geometry is not Euclidean. There is a crucial difference in the way separation between events is measured. In Euclidean space, distance is always non-negative and reflects purely spatial separation. In Minkowski space, the analog of distance, which we call the spacetime interval, blends temporal and spatial separation in a way that carries a different sign structure. Because of this, time does not enter on exactly the same footing as the spatial directions, even though it is united with them in the overall geometry. This sign difference is not a minor technicality. It changes the meaning of geometry itself. In Euclidean geometry, distance mainly tells us how far apart two points are. In Minkowski geometry, the interval tells us something deeper. It helps determine causal structure. It tells us whether one event can influence another, whether a signal moving no faster than light can connect them, whether one can be in the future of the other, or whether they are outside each other's causal reach. So geometry has become more than shape. It has become the language of causality. That is worth repeating. In Minkowski spacetime, geometry encodes causality. This is one of the profound beauties of the subject. The abstract geometry is not detached from physical meaning. It is not geometry for its own sake. The structure of the space tells us which events can affect which other event. It tells us the very architecture of possible influence. Now let us turn carefully to the spacetime interval. If ordinary distance in Euclidean geometry tells us how separated two points are in space, then the spacetime interval is the corresponding relativistic notion for two events in spacetime. But unlike ordinary distance, the interval is not simply a positive measure of separation. Its character depends on the balance between temporal separation and spatial separation. This is where the subject first feels unusual. Two events can be separated in such a way that the temporal part dominates. In that case, one says they are time-like separated. This means, in intuitive terms, that one event could in principle influence the other by a signal moving slower than or equal to the speed of light. A clock traveling from one event to the other could experience the passage of time along that route. Two events can be separated in such a way that the spatial part dominates. In that case, one says they are space-like separated. Then no causal signal, no influence limited by the speed of light, can go from one to the other. Different observers may even disagree on which of the two happened first. Because if causal connection is impossible, the order is not absolute. And then there is the boundary case, light-like separation. This is the case in which a light signal could connect the two events exactly. They lie on the path that light can follow. So the interval is not merely a number. It is a classification of possibility. Time-like, space-like, and light-like. These are not just technical adjectives. They tell us what kind of relation the universe permits between events. Now the next point is one of the deepest in all of special relativity. Although different inertial observers assign different spatial and temporal coordinates to the same pair of events, they all agree on the spacetime interval between those events. This agreement is called invariance. And invariance is more fundamental than coordinates. It is worth repeating slowly. Coordinates change from one frame to another. The interval does not. The observer-dependent description varies. The underlying geometric relation remains. This is a guiding principle throughout modern physics. The deepest truths are often not the quantities that look simplest in one coordinate system, but the quantities that remain unchanged when the coordinate system changes. So when we say the interval is invariant, we are saying that it captures something real about the space-time relation between events, something no inertial observer can alter merely by moving differently. Let us pause and reflect again. If one observer says two events are separated by a certain amount of time and a certain amount of space, and another observer gives different amounts of time and space, this does not mean reality is unstable. It means that the split into space and time is observer-dependent. The underlying space-time relation is stable. That stable relation is what the interval expresses. Now we are ready for the image that perhaps more than any other organizes intuition in relativity. The light cone. Pick an event. Imagine a flash of light emitted from that event in all directions. As time passes, the light spreads outward through space. If one represents space and time together in a space-time diagram, the set of all possible light signals leaving that event forms a cone-like surface. That surface is called the light cone. The light cone divides space-time into regions with very different meanings. Inside the future light cone lie the events that can be reached from the original event by signals moving at speeds no greater than light. These are events that the original event could influence. Inside the past light cone lie the events that could have influenced the original event. Outside the light cone lie events that are space-like separated from the original one. No influence traveling within the relativistic speed limit can connect them. So the light cone is not merely a picture. It is the local architecture of causality. It tells us what future is accessible, what past is relevant, and what elsewhere is causally disconnected. This is worth repeating because it is central. Causality is built directly into the geometry. In Euclidean geometry, a circle around a point tells us which points lie at a fixed distance. In Minkowski spacetime, the light cone tells us which events lie at the boundary between possible and impossible causal influence. It is a much more physically charged object. The language of time-like, space-like, and light-like separation is really the language of position relative to the light cone. Time-like means inside the cone. Light-like means on the cone. Space-like means outside the cone. And because all inertial observers agree on the interval, they also agree on this causal classification. They may disagree about coordinates. They may disagree about elapsed coordinate time or spatial distance. But they do not disagree about whether two events are time-like, space-like, or light-like related. The causal type is invariant. Again, invariance is more fundamental than coordinates. Now let us turn to the rules that connect one inertial observer to another. These are the Lorentz transformations. In classical mechanics, when one observer moves uniformly relative to another, one uses Galilean transformations. Those preserve the idea of a universal time. They assume that all observers agree on simultaneity. But once the speed of light must remain fixed for every inertial observer, those classical transformations no longer work. They must be replaced. The Lorentz transformations are the correct rules for converting coordinates between inertial frames in special relativity. They make space and time. That phrase is often used, and it is accurate. They make space and time. A new observer's time coordinate for an event depends not only on the old time coordinate, but also on the old spatial coordinate, and likewise for space. This mixing is the mathematical expression of the failure of absolute simultaneity. One observer's notion of a purely spatial slice, a set of events regarded as happening at the same time, is not the same as another observer's notion of simultaneity. What one observer calls now across space, another observer tilts into a mixture of here and then. This sounds strange because ordinary intuition is slow-speed intuition. We live in a regime where relativistic effects are small. But in the geometry of spacetime, this is completely natural. The Lorentz transformations are not arbitrary rules. They are the symmetry transformations of Minkowski spacetime. They are precisely the changes of coordinates that preserve the invariant interval. And from this single fact, many famous effects follow. Time dilation follows. A moving clock is found to run slow relative to an observer's coordinate time. Length contraction follows. An object moving relative to an observer is found to have a shorter length along the direction of motion than in its own rest frame. Relativity of simultaneity follows. Events that are simultaneous in one frame need not be simultaneous in another. These are often taught as separate phenomena, but it is better to think of them as consequences of one geometric structure. They are not independent surprises. They are different faces of the same space-time symmetry. It is worth repeating. Time dilation, length contraction, and relativity of simultaneity are not separate axioms. They are consequences of the Lorentzian geometry of space-time and the invariance of the interval. When one truly absorbs that, the subject becomes calmer. One no longer feels that relativity is a bag of paradoxes. Instead, it becomes a coherent geometry. Now let us move to worldlines and proper time, because this is where spacetime begins to feel alive. A worldline is the history of a particle or observer through spacetime. Instead of taking snapshots of an object at different times and trying to connect them mentally, we think of the object's entire existence as a curve in spacetime. If the object is at rest in a chosen initial frame, its worldline goes straight upward through time in that frame, remaining at the same place in space. If the object moves uniformly, its worldline is still straight but tilted. If the object accelerates, the worldline curves. This is a very powerful change in viewpoint. Rather than asking where the particle is now, then where it is later, then where it is after that, we view the full curve as one geometric entity. Motion becomes geometry. Dynamics becomes the study of curves and how they behave. Let us pause and reflect. A worldline is not just a drawing trick. It expresses the simple truth that an object does not merely occupy one place and then another. It traces a path through spacetime. Its existence is extended in time, and spacetime lets us represent the extension geometrically. Now along the time-like worldline, meaning the history of something moving slower than light, there is a distinguished quantity called proper time. Proper time is the time measured by a clock that travels along that worldline. It is, in a sense, the personal time of the object. It is not the coordinate time assigned by some external observer. It is the time experienced along the path itself. This is extremely important. Coordinate time depends on the frame. Proper time does not in that same way. Proper time is geometric. It is determined by the worldline in spacetime. Different observers may use different coordinates to describe the path, but the proper time along the path is an invariant quantity. So again, relativity teaches us to look beyond coordinates to geometry. The most physically meaningful time for a moving clock is not some arbitrary coordinate time, but the proper time recorded along its own history. This is why the so-called twin paradox becomes understandable in spacetime language. Different worldlines between nearby events can have different proper times. The geometry, not any contradiction, explains the outcome. One path through spacetime simply contains more proper time than another. It is worth repeating that motion in relativity is best understood through curves, not isolated snapshots. Worldlines give continuity to the story. Proper time gives intrinsic temporal measure to the story. Now let us widen the language further by introducing four vectors. In ordinary mechanics, one often deals with vectors in space: displacement, velocity, force, momentum. In relativity, because space and time belong together, it is natural to package quantities into objects adapted to spacetime symmetry. These are called four vectors. A four-vector is conceptually a geometric quantity with one temporal component and three spatial components, arranged in a way that transforms properly under Lorentz transformations. That last phrase is important. A four-vector is not just any collection of four numbers. It is an object whose components change from frame to frame in exactly the way spacetime geometry requires. The simplest example is the position 4 vector, which corresponds to the event itself in coordinate form. Then there is 4 velocity, which describes motion through spacetime using proper time as the intrinsic parameter along the worldline. Then there is form momentum, which unifies energy and ordinary momentum into one spacetime object. This unification is conceptually elegant. Things that seem separate in pre-relativistic language become parts of one geometric whole. Let us pause and say this in a quieter way. A four-vector packages time and space into one object because nature respects spacetime symmetry, not separate space symmetry together with an independent universal time. If the laws of physics are to look the same for all inertial observers, then the quantities we use should fit naturally into that symmetry. Four vectors do exactly that. They bring clarity because they separate the invariant object from its frame-dependent components. Different observers may record different components, but they are describing the same four-vector, just as different coordinate systems can describe the same geometric arrow in ordinary geometry. This pattern by now should feel familiar. The object is primary. The coordinates are secondary. The invariant relation is primary. The observer-dependent split is secondary. Nowhere is this more illuminating than in relativistic energy and momentum. In classical mechanics, energy and momentum are distinct concepts, related but separate. In relativity, they are more deeply unified. They become components of a single form momentum. This means that what one observer calls mostly energy and another observer calls a different mixture of energy and momentum are not contradictory descriptions. They are different component descriptions of the same space-time quantity. This is a very modern way of thinking. We stop asking which separate quantity is the absolute one, and instead ask which unified object remains geometrically meaningful across all frames. Now let us speak about mass. In relativity, the invariant notion is rest mass, often simply called invariant mass. It is a property tied to the form momentum in a frame-independent way. It does not grow merely because the object moves relative to a chosen observer. The energy of the object may increase with motion, and its momentum certainly changes with motion, but the invariant mass is not identical to that changing energy. This point is often blurred in popular discussions, so it is worth stating carefully. Rest mass is not the same thing as relativistic energy. Energy depends on the observer's frame. Invariant mass for a single particle is the same for all inertial observers. Again, geometry unifies what seems separate. Energy and momentum are not fundamentally disconnected bookkeeping devices. They are two aspects of one spacetime quantity. Mass is understood not as a crude resistance to motion alone, but as something related to the invariant structure of that quantity. At this stage, let us gather the threads. We began with the question of why spacetime is needed at all. We saw that classical mechanics separates space and time because it assumes absolute simultaneity and a universal time. Special relativity removes that assumption. Once simultaneity becomes observer-dependent, space and time can no longer be treated as fully separate absolute arenas. They must be understood as parts of a unified spacetime. Then we introduced events as occurrences of place and time, and we stressed that an event is independent of coordinates, even though its coordinate labels depend on the observer. Then we moved into Minkowski space, the flat geometry of special relativity, where the crucial difference from Euclidean geometry lies in the structure of the interval. Then we examined the spacetime interval itself, which classifies separations into time-like, space-like, and light-like, and which remains invariant under changes between inertial observers. Then we saw the light cone, the central geometric object that organizes causality, dividing spacetime into what can influence, what can be influenced, and what lies beyond possible causal contact. Then we discussed Lorentz transformations, the symmetry rules that replace Galilean transformations and preserve the interval, giving rise naturally to time dilation, length contraction, and relativity of simultaneity. Then we turned to worldlines and proper time, learning to see motion as a curve through spacetime and time experienced by an object is an invariant geometric quantity along that curve. Then we introduced four vectors, especially for momentum, and saw how relativity unifies space with time and momentum with energy into structures better suited to the true symmetry of the world. And throughout, one lesson returned again and again. Invariance is more fundamental than coordinates. It is worth repeating one last time before we conclude. Coordinates are useful, necessary, and often elegant. But they are not the deepest layer. The deepest layer is the geometric structure that all observers share. Spacetime is that structure. Minkowski geometry is the flat version of that structure. The interval, the light cone, proper time, and four vectors are all expressions of what remains stable beneath changing descriptions. Let us slow down even further now, and end by drawing the whole picture together in a more reflective tone. Special relativity invites us to stop imagining the world as a three-dimensional space endlessly updated by an external cosmic clock. Instead, it invites us to imagine a four-dimensional order of events, where what we call space and what we call time are aspects of a deeper unity. In that unity, every event has its place. In that unity, every observer assigns coordinates, but no observer owns reality. In that unity, light cones stand quietly at every event, separating possible influence from impossible influence. In that unity, straight world lines describe inertial motion, curved world lines describe accelerated motion, and proper time measures the lived duration along a path. In that unity, the old divisions soften. Space and time belong together. Energy and momentum belong together. Geometry and physics belong together. And perhaps that is the deepest com one can take from Minkowski's spacetime. What first appears strange becomes orderly. What first appears paradoxical becomes geometric. What first appears abstract becomes almost visual, almost tangible, once one learns to trust the structure. So when you hear the phrase spacetime, let it not sound like a difficult word invented to make physics obscure. Let it sound instead like the name of a discovery, that the universe is more unified than everyday intuition suggests, and that this unity can be understood with patience, geometry, and care. Let us pause and reflect one final time. The event is real. The coordinates depend on the observer. The interval is invariant. The light cone governs causality. The Lorentz transformations express the symmetry of inertial observers. World lines tell the story of motion. Proper time measures the duration along that story. Four vectors gather separate-looking quantities into single geometric wholes. And Minkowski spacetime is the stage on which all of this fits together with quiet consistency. This is the flat spacetime of special relativity. This is the mathematical language in which high-speed physics becomes natural. This is the geometry in which causality is written directly into the structure of the world. And this is why, when we think carefully enough, we no longer speak of space and time as fully separate things. We speak of spacetime. One unified order. One geometry. One common and far-reaching idea.